Hello and welcome to part 3 in the PDF Scraper tutorial video series. Today we're going to talk about column, wall and pad footing designs. So in the last video we left off after having calculated the column loads, column and wall loads for our model. We're going to use those loads today to perform a series of design tasks within PDF Scraper. So the first thing to look at is going to be columns. So before we do our column design, we need to look at the design properties that are set up for each of these columns. So at the moment, you can see that they're in there just as the default column size. It's automatically estimated the column size from the size of the markup that was imported from the PDF. But obviously, we're going to want a more refined column size than that. So if I go in and I double click on one of these columns, you can see it brings up the column properties window. Some of these we've seen before in the previous videos. For instance, the depth, breadth, whether it's rectangular or not. Others only get used in the design activities. So for instance, the reinforcement ratio, the concrete grade, cover, to name a few. By default, the column is going to be in reinforcement ratio mode. So what that means is that the reinforcement within the column is estimated from this reinforcement ratio parameter here. That'll default to 1%, as you can see here, but you can take that up to 4%. The other thing we can do if we change it in the properties menu is actually to move away from this reinforcement ratio. If we click on the use reinforcement ratio simple, what that'll do is allow us to manually specify the reinforcement in the column. And you can see the section plot on the side here has turned on, and we can now see the reinforcement in there. So we can change the number of bars, the size of the bars, whether it's restrained or not, just in this box down here. And it'll also give you an estimate of the reinforcement ratio just beneath that section plot. We can also change the yield strength of the bars by doing this. For now, I'm going to leave it as reinforcement ratio. Just take the simple approach to start with, and I'll get out of this. So what we're going to do is go straight into doing some column designs. So to do that, all we need to do is go design, check columns, and in this instance, we're going to go check all columns. So it will load. If there was any errors during the column design, it'll pop up and show you. In this case, we don't have any, which means that all of our columns have passed the design checks. So to look at the results of the design check process, we can go into our label data, the little eyeball up here, and we can turn on utilizations for the columns. And if I do that and get out of it, you can see that it gives you a utilization factor against each one of these columns. And what that is, it's the load in the column divided by the axial capacity of that column. So it's a measure of how hard the column's working. And you can see that if I flick through each of these levels, given that our column is the same size at every level, you can see that the utilization goes down as we go up the building, which is exactly what we'd expect. Obviously, the load increases as we go further down, so the utilization is going to increase. We can also get a bit more granularity on the design results if we like, and we can do that by going into the individual column that we want to look at. If we right click on it, we can go inspect capacity. And that brings up the column results dialog. And in this, you can see that the capacity curve of the column is plotted for the two major axes, X and Y. And it also gives you a text output describing the capacities of the column on the side here. So you can see this particular column that we're looking at has a utilization of 0.69, which is backed up by this curve here. So that central dot there is the 8,762 kilonewton axial load, which you can see is our ULS rundown load on the side here. And you can see that sits within the capacity curve, meaning that this column has passed the design check. In this particular instance, this column is quite stocky. So this red line here is the slenderness line is straight and intersects the capacity curve up here. If it were a more slender column, we would find that red line there would actually start to curve. So I might just do that now. If I go in and I change this column to be, say, 300 square, And then I do that same thing again. So I'll go into inspect capacity. And when you go into inspect capacity, it's implicitly doing the design in the background. And you can see that that red line now, instead of being straight for a stocky column, we actually start to see a curve in that red line representing the moment magnification that occurs due to the slenderness of that column. And you can see that that central dot in there no longer exists, and that's because it exists somewhere out in the void. So this column has failed. And you can see that the utilization has now gone red, meaning that that column needs to be rechecked. But if we look in our text output report over here, we can see that it's currently sitting on utilization of 7.27. So it's obviously failed by quite some way. These plots are dynamic, by the way, so we can obviously zoom them around, we can scale them as we want, we can right click and scale them in each axis separately. If we mess it up too much, we can click just in the bottom left corner down here, click that A, and it'll auto scale it back to what it was originally. If we right click on it, you can see there's a few different options that we can do to play with the axis scaling, a few different plot options to show grids, downsample, perform averaging, that sort of thing. Or you can just export either a scalable vector graphics image, an SVG, or a normal image file. So that's columns. We can also do exactly the same thing for walls. So we haven't checked walls yet, but all we need to do that is, again, go design, walls, check all walls. And that'll happen fairly quickly. Now we can do the same thing. We can go into our label data dialog, and under the walls section, we can turn on utilization. And it'll give us a utilization next to that wall. Utilization is obviously exactly the same as for the column. It's the load in the wall divided by the capacity of the wall. And again, if we right click on that, we can go inspect capacity. And it will give us a text output, a text report of the capacity of that particular column. PDF Scraper will give you a shear capacity in this text output report, but obviously, given that we're only dealing with gravitational loads here, we're not assuming that there is any shear in this wall. So that's provided for information purposes only. So the next thing we can do for both columns and walls is to check the fire utilization. So if we go design, check fire, or alternatively, we can click this fire symbol up here. And then we turn on fire adequacy. I'll do it for both walls and columns. Just let me check. Yeah. So you can see that it tells you whether the FRL specified for each of these columns and walls is adequate for the dimensions of that column or not. So by default, we're getting a 90-minute FRL requirement for each of these columns. So it's comparing that to the utilization of that column under the fire conditions. So you can see that all of these are okay. All of the walls look fine. This column that we've reduced to 300 by 300 is obviously struggling. And what that is telling you that the axis distance to the reinforcement is inadequate, and also the thickness of the column is inadequate. The two things are dependent on one another, so you can get away usually with just changing one, and it'll have a beneficial effect on the other. So we can change the axis distance to reduce the minimum width of the column, or vice versa. At the moment, all of our columns are fairly stocky, so I wouldn't expect that we'd have too much of an issue with fire, but I'll just flick through each of the levels. Any erroneous results will be shown in red, so we can quickly flick through, look for any red results, and we can see that there aren't any. So everything works at fire. So there's a couple of other things we can check while we're looking at the columns. The first of those is the transition of load from one column through the slab into the column below. This is generally not such an issue when you've got columns that are the same size at each level, but we've got columns that are changing size with very large loads on them. You can often find that the lower concrete grade of the slab suddenly becomes an issue. So to check that, we just go to design and we go check column transitions. And when you do that, it comes up with this pop-up, It'll tell you if any columns have failed the transition checks and also just give you a few disclaimers talking about how it's actually doing these checks. And what that's trying to say is that all the transition check is doing is looking at the pure overlap area between the column above and the column under, and just figuring out what is the bearing stress that's moving through that region of concrete, and comparing that to the concrete grade of the slab. It also does a check on the confined effective concrete strength of the slab. And it does that by calculating whether that particular column is an edge, corner, central within the slab column, and does the calculation according to AS 3600. So if we get out of this, we can go back into our eyeball. We'll turn off fire adequacy, and let's turn on transition utilization. Here you can see that the top columns, the utilization is 0 because there is no column over top of these, so there's no transition to check. If we go back down towards the bottom of the building, we can see that each one now has a utilization. There's also a code you can see that's associated with each of these transition checks. So there's 3 parts to this code. There's the first one is, in this case, it's an I. That is the confinement condition of the slab concrete. The second one is the assumed grade of the slab concrete, and the third is the assumed thickness of the slab within this check. Where you've got complicated slab geometries and potentially slabs with different concrete grades in the same region, it's just useful to validate that these design values are appropriate for the situation. The algorithm used to do the transition check is relatively simple, so it's just a matter of validating that these values are appropriate. So looking around here, we can see the main one to check is going to be the slab confinement assumptions. So all of these are I, meaning that it's interior. So it's assuming full confinement of the concrete slab. So if we move around this one, for instance, you can see that that's an E instead of an I, indicating that that is considered an edge column. Depending on your view of the world, you may look at that and go, well, I think that's a corner column because obviously there's an edge to the south as well. Or you could look at it and go, well, that edge is far enough away. I actually think, it's only confined on 2 sides. If that's your opinion, you can manually change the assumed confinement, and we do that by going into that column, and we can change this slab restraint box here. So by default, we get it defaults to auto, as you can see, but we can change that manually to interior, edge, corner, or none. And none means that it won't take any effective confinement of the slab, and it'll just do a straight up bearing check on the concrete grade of the slab. And we might be able to look around up here and find a corner column as well. So this one here, for instance, is one that we might want to look at again. So it's automatically calculated as an edge column. In reality, you'd probably call that a corner column. So there's 2 ways around that. We can either go in and we can manually change it from auto to corner. And if we do that, we'd have to redo the check. And I can do that just by right-clicking on it and go and check transition. And you can see that E is now changed to a C, indicating that it's now being considered as a corner column for confinement purposes. The other thing that we can do is go into the Edit Constants menu. So if I go Edit Constants, Design, we can change this transition search diameter. And what that is, it's how far from the column is PDF Scraper looking for an edge. In this case, the default value is 10, and that's a multiplication on the slab thickness. So in our situation here, we have a 200 mil slab thickness. Our multiplier is 10, meaning that it's searching within a 2 meter radius of that column. And likely what is happening here is that if you imagine a circle with a radius 2 meters around that column, it's likely clipping the edge of this corner here, meaning that it's not being considered as a corner column when it probably should. So we could also just change that property in the edit constants menu to make it larger than 10, which would expand that circle a little bit further. So the other thing we can check for columns is going to be punching shear at each level. So we can check that by going design and check column punching. Or again, we can click this this button in the toolbar here, the column punching menu. So it's popped up with an error window telling us that there's a series of columns that have failed the punching checks. And we can get out and look at exactly which ones those are, the same method that we've used before. So we go into a label data box, we'll turn off transition and we'll turn on punching utilization. And as expected, you can see that it's the internal columns that are having issues with punching shear in this case. By default, when PDF Scraper is doing this check, it's assuming that the slab is a post-tension slab with an effective pre-stress that's assisting with the punching shear. If I double click on this slab, you can see there's an effective pre-stress parameter for each of the slabs, and that effective pre-stress is used in the punching shear calculation. So obviously the higher the effective pre-stress, the greater the punching shear capacity. It's important to ensure that should they be RC slabs or there's very minimal effective pre-stress in a given region of slab, that this is adjusted to 0 or a lower value. In this case, we're going to assume it is a PT slab, so I'll leave it at 1.5. So we can flick through and we can see there's a few slabs that are failing in punching. So to get around that, we might decide that we want to increase the size of the column. We might decide that we need a drop cap at a particular level to help with our punching shear, or we might want to go into a bit more detail and do a punching check elsewhere to try and validate that it might actually work. So it is using a moment when it's doing its punching check, and that moment can be input in the column properties box. So we can put in an MX and an MY moment. That'll be used both in the design of the column itself and in the punching shear check. I'm going to leave these columns for the moment. In reality, we would, this is the point where we might do something about these punching failures, but for now, I'm not going to worry about it too much. So the next thing I want to move on to is footing design. So if we flick down to our footing level, I might just turn off the PDF background here so we're not getting confused. And I'll turn on column overs as well. And just turn off the tags. All right. So similar to what we've done before, we can either go design, check pad footings, or we can click this end button at the end here. So check pad footings. And again, it's going to tell us which footings have failed the design checks. So similar to before, I'll go to the label data and I'll turn on, in this case, there's two utilizations that we're interested in for the pad footings. There's the bearing utilization, so the geotechnical utilization of the soil, and then there's the structural utilization of the pad footing. So that's bending, shear, punching. So I'm going to turn both of those on. Right, so we can see that almost none of these pads are working. And the reason for that is obviously we haven't sized these pads. These are just the default size that we drew them at in the PDF markup. So it's not surprising that they're not working. As with columns and walls, we can right click on a pad and we can go inspect capacity, which gives us a text report of the capacity of our pad. So this gives us a bit more granularity as to what, when we say the structural utilization is, in this case, 1.38, it tells us what exactly is failing. So we can see that the 1.38, so the critical utilization is the shear in the W direction. And you can see that it breaks down the capacities for each of those elements I was talking about before. So bending in two directions, shear in two directions. and also the column punching through the pad. So at this point, it's a good time to talk about optimization. We'll start with pad footing optimization and we'll move on to column optimization after this. So what the optimization allows us to do is it allows us to look at the load on a given pad footing and size that pad footing appropriately for that load without having to manually go through each footing and decide on what size it needs to be. So all we need to do to optimize our pad footings is we go design, optimize, and we'll go optimize all pads. And you can see that that's increased or decreased the size of all the pads depending on the axial load in the column. So if I just go up to my label data, I'll turn off our utilizations and just chuck on the size of these pad footings for a second. So it's obviously sized both the width and the length of the pad, but also the depth. So it's sized the depth to avoid punching and shear failures within the pads, and obviously to avoid the use of ligs in the pads as well. So by default, it doesn't assume that there's any lig requirement in the pads and just sizes the depth so that the concrete capacity in shear is adequate. In this case, pad footings probably look quite large, and the reason for that is the default soil bearing capacity. So if I run into here, you can see that the bearing capacity for each of these pads is 250 kPa, which is obviously not amazing. So what we can do, say we've already imported our markup and we want to change the bearing capacity of these pads. All we can do is we can turn off the column and wall structure. We'll select all of our pads. We'll right click properties and we'll just change that soil bearing pressure to 500. When you've got multiple objects selected like this and you go into the properties box, you can see that some of the values default to some strange value, in this case 1. Generally all that means is that there's varying values for each of those in each of the objects that you've got selected. If you don't change that, then it's not going to change. It's not going to change the pad footing width to 1. So because the only parameter that we've changed in this case is the bearing pressure, that's all that will be changed. So we've changed that to 500. We'll go OK. And then let's just rerun our pad optimization. Right, and you can see that that's now a lot smaller. And obviously when you think about it, particularly the depth of the pad footing is highly dependent on the size of the column that sits on the pad. So actually I've done this probably in the wrong order. I've optimized the pads before the columns. In reality, you'd size your columns and then you'd use that column size to appropriately size the pad so that the punching shear and shear and bending checks consider the appropriate sized column. So on that note, let's now have a look at column optimization. So I'll just flick up to level 2 and I'll turn on column sizes. So as with pads, all we need to do is go design, optimize, and we will optimize all columns. And that can sometimes take some time, but if we let it run, you can see that it's adjusted the sizes of each of these columns to resist the load applied to that particular column. So it's going to use, in terms of whether you get a rectangular or a circular column, it's going to use the setting that existed before the optimization. So we look at this one. I've actually got a couple selected here. So this one is set to be rectangular. If I were to uncheck that, make it circular, then when it optimized, it would be optimized to a circular column. The other property that is critical when performing the optimizations is this target aspect ratio parameter. And again, that one is estimated from the markup aspect ratios in the PDF that you've imported, and it'll calculate that based on how rectangular the markup is. So in this case, it means that we're looking for a slightly larger depth than breadth. So that ratio is the target depth divided by breadth. So if we were after a larger depth, so one that was slightly taller than it was wide, we have a value larger than 1. If we're looking for something the other way, we might be looking for a value less than 1. If we're after a square column, then we just make that 1. So at the moment, I'm going to leave it with the target aspect ratio that is already there. Because we use the same column markup for each of these columns, they'll all have this 1.231. So you can see that they're all slightly rectangular. But similar to what we did with pad footings, we can select everything and change that target aspect ratio if we like. So at this point, now that we've got our column sizes locked in, we would go ahead and redo the transition and punching shear checks that we did previously, because again, obviously they're dependent on the size of the column. You may also want to do some column rationalization, and an easy way to do that is to use the Format Painter tool. So we can do that by selecting a column, say, let's use this 400 by 350 column here. So I can select that. I'm going to select the Format Painter here, and then all I need to do is just go and click on these columns, and it'll just paste the format of that column, so the size and some of its parameters to the column the cell we're clicking on. And we can do that just to rationalize the column sizes on a particular level a bit. Another way that we can do this column size rationalization is through the use of column types. To set up a column type, I can double click on this column, and you can see that this box up here, it's by default it's set to custom. And custom can be read as no type. It means that all of these parameters you can set individually for each particular column that has this custom type. But say we want to set up a type and use this type over and over again on a bunch of different columns. What we can do is either select a column from this drop-down list. In this particular instance, we have no other column types set up. So otherwise, we can just click Add Type. And then when we say Add Type, we're presented with this dialog here, and we can put in the parameters of the particular type that we want. So in this case, let's use a 400 by 400 column. We'll leave it at a 1% reinforcement. And for the purposes of optimization, let's just make it a square. So we'll set the target aspect ratio to 1. We can also specify manual reinforcement for the column types, as we sort of discussed before, but I'll leave it for now. And let's change the name of our column type to, let's call it my type 1. And then I'll go OK. So when we do that, you can see that the type parameters box gets grayed out. So we can no longer, for this particular column that we have selected, we can no longer change the type parameters, because obviously they're dictated by the column type. We can, however, change the instance parameters, because even if a type is assigned, the instance parameters are dependent on a particular column only and not on that column's type. All right, so I'll get out of that. We'll go OK. If I go back up to my label data dialog, I can turn on column type. I'll turn off the size. Right, so you can see that most of them are custom, and then this one that we've created here, our 400 by 400 column, is my type. I might actually just turn on sizes quickly, might make this a bit clearer. So as before, I'm going to use the Format Painter. So I'm going to select that column, I'm going to go Format Painter, and then I'm just going to click on a couple of columns around the place. And you can see that when I do that, the type changes from custom to my type 1. So the type property is being copied over when I format paint to each of these. So that's all well and good now, so that we know that each of these columns are of a particular type. The real strength of using types in this way is that, for instance, if I now decided that actually I wanted that type to be 500 by 500, I can go back into that. I can go edit type. So my type, I'm going to edit type. And then say I'm going to change that to 500. 500 by 500. I now want it to be a bit larger. We'll go OK. OK out of this property. And you can see that all of the my type 1 columns have now been changed to 500 by 500 in size. So it's effectively a way of grouping columns as well. So we can just change that one column type, and all of the associated columns with that type, their size will also change. And obviously any type parameter that you can set is also going to be changed within any of the columns with that type. So that might be the reinforcement, the concrete grade, anything that we can change. So we can also use types for pad footings. So in exactly the same way as I've just done for the columns, I can go into the properties dialog of a particular pad footing. I might actually just turn on, if I go to our label data, I'll turn on the footing types first. Again, you can see that they're all defaulting to custom type, which you can see here. We've got no types created already, so add type, and we'll call this one my pad 2. Let's make it 3500 by 3500 with a bearing capacity. A bearing capacity is a instance parameter, obviously allowing for potentially different soil stratas within the site. So I'll leave this as a 3500 by 3500 by say 1200 pad footing. And then if I go OK, again you can see that the type parameters box has been grayed out. We can no longer change the type parameters for this pad. Using this pad type drop down at the top here, we can change that back to custom if we like, and then we can change these type parameters now that is no longer a type associated with this footing. But I'm just going to flick that back to my pad. And if I go OK, you can see that the type listed for this pad is now my pad 2. So similar with the columns, I'm just going to select that. I'm going to format painter, and I can just paint that pad footing type around the place. Obviously, you would use multiple pad footing types at a given level. In this case, I'm just going to click everything just to make it easier. The other way we can do it is that, so instead of using format painter, we can just double click on a particular pad and use this drop down. So we can just change that to my pad 2. And then from any dialog box, we can remove the type, which would delete my pad 2 entirely and force each of these pad footings that have that type currently back to custom pads, or we can edit the type. And then any changes that we make in here will be populated through to all of these footings with that pad type. There is an easier way to create pad types though, and I'm going to run through that now. So all I'm going to do, I'm just going to select all of these pads. I'm going to go to Tools, and I'm going to go Auto Create Pad Types from Selection. And what that is going to do is it's going to try and automatically group pad footings based on the axial load on the column sitting on that pad. And all we need to tell it is how many different types of pad footings do we want to create. And this is up to the engineer. I would hope that you would have some intuitive sense of how many pad footings, how many pad footing types that you might like to have on your project. In this case, I'm going to leave it at the default value of 4 and go OK. Right. Now, you can see that that's created 4 new pad footing types. We've got PF1, PF2, PF3, and PF4. And loosely, we can see that PF4, so the larger footings, are towards the center of the structure. And then the footings around the perimeter, which are less heavily loaded, the smaller pad footings, so your PF3s, your PF2s. So intuitively, this looks correct. And if we check footings and bring up our footing utilizations, you can see most of them are working at a fairly reasonable utilization. So it's done quite a good job in this case at grouping the pad footing types based on the column loads. And you can play around with how many pad footing types you like. So all I need to do is select that, select them all again, and I can do exactly the same thing. Maybe 4 was too many. Maybe I'm going to knock it down to 3. Maybe I want to knock it up a bit. It's completely up to you. And we have exactly the same functionality available for the columns. So I'm just going to go to one of the upper levels. Let's just turn off slabs. tributary areas. We'll get rid of the transfers, trip lines. And I'm just going to select everything here. So I've selected all these columns. I'm going to go Tools and then Auto Create Column Types from Selection. Now that's going to create types for all of the columns within the selected chains. So obviously in this case, I've only got one level selected, but all of the columns forming part of these selected chains will also have column types created. And in this case, I'm just going to do the same thing. I'm going to create 4 column types. So I'll click OK, let it do its thing. Great, and you can see that we've now got 4 column types. We've got CT1, 2, 3, and 4. And if we were to do the same thing, we were to look at the column utilizations, we'd see that they'd all be working, ideally at sort of 70, 80, 90% utilization range. So we've got a particularly efficient structure without using too many unique column forms. So that's really all of the main design operations I wanted to show in today's video. I'm just going to touch on a few little miscellaneous pieces of functionality that you might find useful. The first one is going to be the tabular column editor. So if we go Edit, we just go Tabular Column Editor. What that's going to do is it's going to bring up a table with all of the columns on the structure in it. And you can sort these just by clicking at these headings at the top here. We can sort them by chain. We can sort by level. RL, which is going to give you a similar result to level. You can sort by any of these parameters. And any of these parameters that you can see here are changeable within the tabular column editor, except for, you can see these ones that are grayed out. And the reason they're grayed out is because these are columns that have a column type assigned. So similar to how what we were seeing in the column properties box, where when you set a type for a column or a pad footing, the type parameters are no longer adjustable. We're seeing the same thing here. So all of these represent type parameters, and we can't change them because there's a type set for this column. What we can do is that in the type column, we can right click on that, and that'll give you a drop down list of all of the options available. What we can do, we can change it back to custom, and then once we do that, we can change all of these type parameters. If we keep scrolling horizontally, you can see that we get to instance parameters at the end here. So even these columns with types assigned, once you get into the instance parameters, you can start changing things again. Any cell that has a yellow highlight means that it's a multiple choice cell. And how you select from those multiple choice items is that you just right click on that cell. And when you right click, you're presented with a series of options. So in this case, these are all of the standard bar sizes that we can choose from. And you can change any parameter that you can access from the column properties box. You can also access from the tabular column editor. So the next thing we're going to talk about is the wall group analysis. So what we're going to do is we're going to select a bunch of walls. I'm going to right click and I'm going to go set wall group, and we're going to create a new group. It'll default to something like core. Let's just keep that for now. And all we need to do to access that is go edit. Where is it? Wall groups, edit wall groups. And you can see that we're presented with a wall group dialog. And that lets you select from any wall groups that you've got set up within your project. And you can view each level of those wall groups. So when we created this wall group here, when we selected these walls, we implicitly added that entire chain into a wall group, which is why this core wall group is accessible at multiple levels. In this particular project, the core is the same at every level, so you can't see it changing as we flick through the levels. But in a more complicated building, you might see that core changing as you go up, and then you can access the properties of that core box. So the area, the I value, Z value, principal axes, that sort of thing. The other thing we can do for wall groups is that we can use them to bulk export wall loads. So if we go export load summaries, and we can export wall group loads, and that all that's doing is it's summing all of the loads from each of the walls within that wall group and exporting them as a group load as opposed to individual wall loads. And the last little piece of miscellaneous functionality I just want to touch on is the static earthquake designer. So all we do is go design earthquake. It's going to bring up this dialog here, which is relatively simple. But what it's doing is a earthquake load calculation to AS 1170.4. So based on the loads that have been calculated as part of these analyses that we've done previously, it'll use those loads to calculate the seismic mass of the building at each level. And you can adjust the factors for each of the types of loads to generate that seismic mass. So it's going to default to the AS 1170 defaults, which is to say a factor of 1 on the dead load and a factor of 0.3 on the live load. But obviously, depending on the usage of the building, the type of the building, that live load factor may vary. Or, if you're unconfident about the SDL, you might want to reduce that to more accurately represent the dead load on the building at the time of an earthquake. We can also change various parameters to do with the earthquake loading. So subsoil class, return period, hazard factor, and then the ductility and performance factors of the building. And then that's just going to calculate an equivalent static, so a type 2, according to 1170 earthquake load at each level, and then show you the cumulative shears and moments and plot them for you on the side here. You can also export them into a Excel spreadsheet just by clicking this export load table button in the bottom corner here. And with that, we'll wrap up today's video. I hope you enjoyed the video tutorial series. And if anything still isn't clear, then feel free to get in touch with us via the form on our website. Thanks for watching, and I'll see you next time.